Hi everyone, I welcome you all for today's lecture on semiconductor memories. Myself, Dr. Muralidharan J, Associate Professor, Department of Electronics and Communication Engineering, KPR Institute of Engineering and Technology, Coimbatore. Let us start with the basics of the semiconductor memories. When you look at the diagram, we can identify that semiconductor memory structure consists of 2 power n row lines and 2 power m column lines. Each row and column interconnected through the memory cell which was mentioned at the middle of the block with square shape. We can do either read or write operation on memory cells. The process of storing the new data on the memory cell, we call it as a write operation, where the data taken out from the memory cell, we can call that as a read operation. We need to select the memory cell address where we need to want to write or read the data operation. The address of the memory cell selected by the row decoder and the column decoder. Basically, the classification of semiconductor memories are classified into read-only memory, we call it as a ROM. Random access memory, we call that as a RAM. Under the read-only memory, we have masked program, programmable ROM, erasable PROM, electrical erasable PROM. Under the random access memory, we have static RAM as well as dynamic RAM. We call these two things as SRAM and DRAM. Let's move on to the static RAM construction. On the left hand side, we can see that it's a 1-bit SRAM cell construction where your inverter was connected back to back. We call that as a static memory, and also this can be called as a bistable. On the left hand side and right hand side of the two inverters, we have bit line which will be used for accessing the data as well as writing the data. On the right hand side, we can see 6 transistor CMOS SRAM cell. This was connected with the help of inverter as well as additional transistors were added to the circuit. Let us see this in detail in the next slide. Now let us move on to the SRAM operation principle. The circuit will be storing 1 bit of data using bistable latch formed with a cross-coupled inverter. Generally, the SRAM cell mainly consists of 4 main parts. First one is the bistable latch, or we can call that as a static memory. The green box represented in the diagram will be represent the static memory cell. It was formed by two cross-coupled inverters. First M1 and M2, which will be a NMOS transistor, which will be forming a pull-down network. Another one is a resistor R, or you can call that as a PMOS load, which will be forming a pull-up element which is connected to the power supply, that is VDD. The outputs V1 and V2 are connected to each other in feedback path. Because of this cross coupling, the circuit has two stable states. V1 is equal to 1 and V2 equal to 0, that is the first one. Another one is V1 equal to 0 and V2 equal to 1. This allows the cell to store 1 bit permanently as long as power is supplied. The next part is access transistor, where M3 and M4 are going to act as an access transistor. They connect the memory cell to the bit lines. These transistors are controlled by the word lines, which we have mentioned as WL. Whenever the WL is equal to 1, the cell is connected to the bit lines. Whenever we are saying WL is equal to 0, the cell will be isolated from the circuit. The next part is bit lines. You can see in the diagram it was represented with the C as well as C bar. C is the bit line and C complement is also another bit line used for either reading the data or writing the data. The capacitance CC and CC bar represent the bit line capacitance. The fourth part and the last one is the pull-up transistor, where you can see MP1 and MP2, which are going to act as a pull-up transistors which is connected to your VDD. They help charging the bit lines before the read operation. Now let us look into how the write operation is carried out in your static RAM. Purpose is we need to store a bit either 0 or 1 in the cell. What are the steps involved is, first step is decide data is to be placed on the bit lines. To write 1, we need to keep BL is equal to 1 and BL bar is equal to 0. Next one is the word line, which is represented the WL has to be activated. Next one is M3 and M4 should be turned on, which is connected in the cells to the bit lines. The stronger bitline driver overrides the previous value available in the latch. When WL becomes 0, the value is stored in the bistable circuit. When we look into the read operation, the purpose is we have to retrieve the stored data in the memory. So what are the steps involved in this? First one is both your bit lines are pre-charged to VDD, that is your power supply. Second one is the word line has to be enabled. Third step is the stored node slightly discharges one of the bit lines through either M1 or M2. The fourth step is a sense amplifier detects the voltage difference between the BL and BL bar. The stored data is determined. For example, if V1 is equal to 1, V2 should be equal to 0. So BL stays high and BL bar discharges. We have seen read and write operation. Now let us see the hold operation also. When word line is equal to 0, the access transistors M3 and M4 will be in off. The cross-coupled inverters maintain the stored value indefinitely. Here, no refresh is required also. Now let us move on to the dynamic random access memory, which we call it as a DRAM. The diagram here representing the 1-bit DRAM cell. It stores 1 bit of data using capacitor and a transistor. When you look at the diagram, you can find one transistor available, which is mentioned as M1, and you have the two capacitors. One is represented as C, another one is CC. Along with this, you have bit line and data in and data out. Whenever CC is much greater than C, your data in and data out process will be taken place. And you can also see the read and write operation selection line is available in the circuit. Now let's move on to the DRAM construction. The DRAM cell consists of the two main components. One is the access transistor, where it was mentioned as M1. M1 is a MOSFET transistor. Its gate is connected to the word line. Either it can take care of the read or write select operation. It acts as a switch that connects the storage capacitor to the bit line. The second one is the storage capacitor. The capacitor C will be storing the data as in form of electrical charge. If the capacitor is charged, then we can consider that as a logic 1. If the capacitor is discharging, then we have to consider that as a logic 0. The third one is the bit line, which was represented using the alphabet D. The bit line D is used for data input and output. It connects the memory cells to the sense amplifier. The fourth one is the bit line capacitance, which was represented as CC. This bit line capacitance represents the parasitic capacitance of the bit line. Usually, the bit line capacitance is much greater than the C, so meaning that the bit line capacitance is much larger than the stored capacitor. Let's move on to the write operation first of the DRAM. The purpose is we need to store a data in the capacitor. The steps involved in this write operation are: first one is the data should be placed on the bit line T. Next step is the word line R should be activated. Next, the transistor M1 will be turned on. The capacitor charges or discharges depending on the input data. If the bit line is high, then capacitor will be charging, and we can understand it's a logic 1. If the bit line is low, the capacitor will be discharging, so the logic will be 0. Fifth one is the word line is turned off and isolate the capacitor and storing the data. Now let's discuss the read operation. The purpose is we need to retrieve the stored data. What are the steps involved in this are: the first one is the bit line is pre-charged to the reference voltage. Next is the word line R should be activated. Third step is the capacitor shares its charge with the bit line. Fourth one is this will be causing a small voltage change on the bit line. So the sense amplifier will be able to detect this change and determine whether the stored bit is 0 or 1. During the read operation, the stored charge is partially lost, so the data must be restored, or you can say that it's refreshed. Now let's discuss 3-transistor DRAM cell. The 3-transistor dynamic RAM cell is used to store 1 bit of data. It uses 3 MOS transistors. From the diagram, you can see that M1, M2 and M3, and one storage capacitor is C. The circuit also includes pre-charge devices like MP1 and MP2 for preparing the bit lines before the read operation. So the characteristics of the 3D RAM is stores 1 bit using 3 transistor and 1 capacitor. It also do the performance of read and write in a different path. So faster read operation than 1T DRAM. Requires periodic refresh because capacitor charge leaks. The most important part of the 3T DRAM cell is first one is the transistors. Let us consider M1, which will be used for write access transistor. It will connect the write bit line, that is data underscore in, to the storage line, controlled by the write select, that is your WS signal. Second one is M2, which is your driver or pull down transistor. The gate is connected to storage node, which is VB. It also controls discharge of the read bit line during read operation. The third transistor is M3, which is used for read access transistor. It connects transistor M2 to the read bit line, that is your data out, and also controlled by the read select line signal. The second one is the storage element, that is your capacitor C. It stores the data as in the form of electric charge. The charged capacitor will be having a logic 1, and the discharged capacitor will be notifying it is a logic 0. Third one is the bit lines. So data in bit line, which is used during the write operation. The data out bit line will be used during the read operation. The fourth one is the pre-charge circuit, where MP1 and MP2 PMOS transistor will be acting as a pre-charge devices. It is also controlled by the PC signal. They charge both bit lines to VDD before the reading process. Let's start the write operation on the 3T DRAMs. The steps involved in the writing a data is first one is write select, that is WS signal has to be high. Then the transistor M1 should be turned on. Data from the data input is applied to the data in bit line. The data is transferred to the storage node VB and stored in the capacitor C. Let us consider the case 1, that is writing a logic of 1. So the data in should be high, the capacitor C should be charges, and the storage node, that is VB, should be approximately equal to VDD, that is for power supply. Now let us consider the case 2, writing a logic 0. The data in should be equal to low, the capacitor C should be discharging, and the storage node VB should be approximately equal to 0, that is your ground level. The stored charge represents the stored bit. Now let us discuss on the read operation of the 3T DRAM cell. Before reading, the pre-charge circuit should be activated. Step 1 is pre-charge phase, where your PC signal turns on MP1 and MP2. Both bit lines are charged to VDD. Step 2 is the read phase. The read select, that is your RS line, should be equal to high and the transistor M3 should be turned on. The read bit line data out is connected to the transistor M2. Let us consider the case 1, that is stored data is equal to 1. If the stored data is equal to 1, then the node VB will be equal to high and M2 transistor is turned on. The current will be started flowing from the bit line to the ground. The bit line voltage will get drops out since amplifier detects it as a logic 1. Let us consider the case 2, where stored data is equal to 0. If the stored data is equal to 0, then the node voltage of VB will be equal to low and M2 remains off. So the bit line stays pre-charged high. So the output will be interpreted as a logic 0. Let's discuss content addressable memory, which in general we call it as a CAP. So diagram given here represent the basic structure and operation of the content addressable memory. The content addressable memory has inputs such as address, data or key, and control signals like read and write. So during the write operation, the address input selects a specific memory location and the given data is stored in that location, similar to SRAM. So during the read operation, the data input acts as a search key instead of an address. So the CAM compares this key with all the stored data simultaneously. So if the match is found, then the match output becomes high 1, otherwise it remains as low. Thus, the CAM performance searching based on content rather than address. The diagram shows how CAM is used as a translation leukocyte buffer for fast address translation. The virtual address is given as the input to the CAM and it treated as a search key. The CAM stores recently used address mapping and compares the input virtual address with all the stored entries in parallel. If a match is found, it indicates a TLB hit and the corresponding physical address is obtained from the SRAM array. If no match is found, then the result in a TLB miss and the system must access the main memory page table, which is taking long time, which will be slower. So thus, CAM enables high-speed address translation in the process. Here the diagram will be showing the internal structure of the single CAM cell. The cell consists of an SRAM storage unit formed by cross-coupled inverter that store 1 bit of data. It also includes access transistors connected to the bit lines for read and write operation. In addition to the storage, the cell contains a comparison circuit that compares the stored bit with input search bit. The match line is initially pre-charged to the high value, and if the stored bit matches the input signal, the match line remains high, so it is indicating a match. If there is a mismatch, then the match line is discharged to low. Hence, each CAM cell not only stores the data but also participates in the parallel comparison. Here the diagram will be illustrating the structure and working of a 4x4 content addressable memory array, which consists of 4 rows and 4 columns in the CAM cell. The structure of the CAM array will be like the array is made up of multiple CAM cells arranged in rows and columns. So each row will be representing a stored word and each column representing a bit position of that particular word. Therefore, a 4x4 CAM can store 4 words of 4 bits each. On the left hand side, the row decoder is present, which selects a particular row during the write operation based on the input address. At the bottom, the column circuitry is used to provide the data input as well as control read or write operations. Now let us discuss the write and read operation of the content addressable memory. So during the write operation, the address input is given to the row decoder, which activates one specific row. The data input is then passed through the column circuitry and stored the selected row in the capsule. So this process is very much similar to writing a data into the SRAM. So in the read operation during the search, the input data is treated as a search key and is applied to the column simultaneously. So each capsule compares its stored bit with the corresponding input bit. So all the comparison in the row are combined to produce a match signal for that particular row. So this is how your read operation, write operation will be performed in your content addressable memory.